Batteries are everywhere around us. Right now, there is probably at least one battery near you, whether it's in your phone, laptop, or another device. But have you ever wondered about the health of these batteries? Have you ever tested the health of a brand new battery? Just because a battery charges properly doesn't necessarily mean it's in a good health. Knowing the state of health of a battery is crucial for ensuring the reliability of your devices and appliances. But how do you measure the state of health? That's exactly what I will be exploring in today's video, so let's dive into details. First, let's define two key terms: state of health and state of charge. Battery state of health refers to the overall condition and capacity of a battery compared to when it was brand new. It reflects how much the battery has aged or degraded over time and tells you how effectively it can store and deliver energy. Battery state of charge, on the other hand, represents the current energy level of the battery as a percentage of its full capacity, essentially, how charged it is at a given moment. In short, the state of health is about the battery's long-term performance and usability, while the state of charge is about its immediate energy level. Here is a quick example. This lithium battery cell was initially rated for 2000 mAh. When its state of health drops to 20%, it means the battery can now only hold 20% of its original capacity, just 400 mAh, requiring frequent recharging. A while ago, I watched a YouTube video about reusing lithium cells salvaged from devices like disposable electronic cigarettes to create portable battery packs. The idea was brilliant. Those devices often have functional batteries even after their primary use. However, there is a catch. If a salvaged cell has a poor state of health, it won't last long. Imagine collecting 4 used cells to build a battery pack, and one of them has a state of health at 20% or lower. Even if the pack appears fully charged, that one weak cell will severely impact the pack's overall performance due to its poor capacity. This got me thinking, how can we prevent this kind of issue? I decided to research how to measure a battery state of health effectively, especially since this feature exists in smartphones where you can see an estimated percentage of your battery's lifespan. It's important to note that this is entirely different from the battery state of charge. During my research, I came across a circuit board from SparkFun called the Battery Babysitter. It integrates the BQ27441 as a fuel gauge alongside with the BQ24072 as a battery charger. This circuit is excellent for monitoring battery charge and health, but it requires connection to a microcontroller-based development board like an Arduino to read the battery data through the I2C port and display it on a PC. This inspired me to create a more compact and self-contained solution. My idea was to design a circuit board that combines all these features in one. So all you need to do is connect the battery and plug in the power. I decided to stick to the same design concept from SparkFun, but with a few modifications. Both ICs, the BQ27441 and the BQ24072, will be used. I will add an AVR microcontroller like the ATmega328, my personal favorite, for data collection. I also include LED indicators to display the battery's state of charge and state of health in real time. Additionally, my design will feature multiple battery connection options and a USB-C connector for modern compatibility. With these goals in mind, I moved on to preparing the schematic. The circuit will have the BQ24072 handling battery charging and BQ27441 monitoring the battery status, including state of charge and state of health. The BQ27441 will send this data to the ATmega328 via I2C, and the microcontroller will drive two 10-pixel LED bars to display the state of charge and state of health percentages visually. Now let's take a moment to understand how the fuel gauge measures the state of health of a battery. The BQ27441 continuously monitors the battery's maximum available capacity, known as full charge capacity, during operation and charging cycles. The FCC reflects the battery's current ability to store charge. It then compares the FCC to the battery's original design capacity and calculates the state of health as a percentage by dividing the FCC by the design capacity. For the state of charge, the BQ27441 uses a combination of column counting and voltage-based estimation. It continuously tracks the current flow into and out of the battery by measuring the voltage across a current sense resistor, and integrates this current over time to calculate the charge. The state of charge is then determined by dividing the remaining capacity by the full charge capacity. Considering its price of around $1.54 and its extensive functionalities, this IC truly deserves a 5-star rating. Now let's move to the charging IC. The BQ24075 is a $1 linear battery charger IC designed for safely and efficiently charged single-cell lithium-ion or lithium polymer batteries. One of its standout features is its dynamic power path management, which allows the system to operate while the battery charges, even under limited input power. The IC includes several intelligent charging features like pre-charge phase. If the battery voltage drops below 3 volts, the IC applies a low pre-charge current to safely wake up the battery. And the battery temperature monitoring, it works with an external thermistor to ensure charging only occurs within a safe temperature range. Thanks to its compact design and versatile capabilities, the BQ24075 is a perfect fit for portable devices. I prepared my circuit schematic using Altium Designer, organizing the project with an hierarchical design. The battery charging and monitoring stage is placed in the independent parent sheet, while the microcontroller and LED stage are contained in a child sheet. This structure makes it easy to reference the parent sheet if you're only interested in integrating the charging stage into your circuit. To keep the parent sheet well organized, I divided the charging stage into sub-blocks. For your convenience, you can search for the required components on Octopart, where you can download CAD files and compare prices and availability. I've also added comments to the schematic sheets to explain the purpose of certain components such as resistors that configure the fast charge and current limit, along with other important notes. To make this project accessible, I've shared the schematic files via the Altium 365 tool. This cloud-based platform allows you to view the design files online. Check the video description for a direct access link to the project files. All you need to do is click the link, send me an access request, and I will approve it. You can even leave comments directly on the schematic. If you have questions or need clarification, I will respond as quick as possible. After completing the schematic, I transformed it into a PCB design. While the PCB shape is randomly designed, I focused on keeping it as compact as possible. Most of the components are small and strategically distributed to ensure easy assembly. Before moving forward, I'd like to highlight an important feature. I've provided multiple connection methods for batteries. The PCB includes a 18-60-150 battery holder and 2.5mm GST connector, and a screw terminal allowing you to connect different types of batteries. However, it's important to note that only one battery should be connected at a time. For the LED indicators, I arranged the 20 pixels into two bars of 10 pixels each. The first bar displays the battery's charging state, while the second bar shows the battery's state of health. Additionally, I added a USB-C connector at the edge of the circuit along with a low capacitance ESD protection circuit and a CH340 USB to serial converter for reliable communication. Here is a quick 3D view of my circuit design. It looks well arranged overall, but I believe there is always room for improvement. Feel free to share your thoughts or suggestions in the comments section below. After finalizing my design, I generated the circuit's Gerber files and uploaded them to JLCPCB for PCB production. For this order, I selected a vibrant purple color for the PCB. Additionally, I ordered a PCB stencil, which is a highly effective tool for precise solder-paste application. I customized the stencil size to match my PCB dimensions and added everything to my cart. Since I needed a housing for the charger, I designed one with minimal screws to simplify assembly. After completing the design, I generated the STL files and uploaded them to JLC 3DP to place my 3D printing order. I configured the material, surface finish, and other parameters before adding the parts to my cart. I then paid for everything to be delivered conveniently in one single package. 6 days later, I received this iconic blue box from JLCPCB containing all my items, the PCBs, stencil, and 3D printed parts, all in excellent condition with a great surface finishes. To streamline the solder paste application process, I also 3D printed a PCB holder. This tool will be particularly useful for double-sided assembly, ensuring efficient solder paste deposition even after assembling one side. Next, I carefully placed the surface-mounted parts onto the PCB. At this stage, tweezers are essential as we are dealing with extremely tiny components. To complete the soldering process, I used my Miniware hot plate, which provides precise heating for an even and reliable solder finish. Here is a microscopic view of the soldering process captured through my digital microscope camera. For your convenience, I've listed all the tools I used in the description of this video. Alternatively, you can skip this manual assembly process by having the circuit assembled directly by JLCPCB, as I've included the Gerber file, bill of materials, and pick-and-place files in the project's GitHub repository. Moving on to the bottom side of the PCB, I used the Assembly Aid tool I 3D printed earlier to securely hold the board while depositing solder paste. Once the solder paste was applied, I carefully placed the bottom side components, again using tweezers, since the LED pixels of the indicators bars are as small as 1 by 1 millimeter. Since the top side was already assembled and could not be placed on the hot plate, I used a reflow hot air gun to solder the bottom side components. After assembly, I cleaned the board with flux removal solvent to ensure a clean and professional finish. During the final inspection, I tested the circuit at various points to check for any short circuit. I noticed some soldering issues around the USB connector, so I carefully reworked the joints. Remember to always use flux and ensure your soldering iron tip is clean. The next step was uploading the Arduino bootloader via the ISP port that I designed in the circuit. For this, I used my USB ASP programmer. Thankfully, the bootloader uploaded successfully on the first try, which was incredibly motivating. However, when I connected the circuit to my computer via USB to upload a test code, the connection failed. After troubleshooting, I discovered that the issue was the CH340 IC. It couldn't establish a connection. I revisited the datasheet and realized that the 3-volt 3-pin of this IC needed to be decoupled to ground using a 0.1 microfarad capacitor. To resolve this, I updated my circuit design and revised the PCB layout accordingly. I then manually soldered the decoupling capacitor between the 3-volt 3-pin and ground on the existing board. For those following this project, you won't need to perform this step, as the Gerber file in my GitHub repository has already been updated to include this fix. Once the capacitor was added, the chip was successfully recognized by my computer. From there, I uploaded a simple test code and the LED pixels worked flawlessly. Encouraged by this success, I proceeded to upload the battery testing code to the circuit board, completing this stage of the project. Next up was assembling the circuit housing. As I ordered the 3D printed parts from JLCPCB, all I had to do was adding 2mm threaded inserts and use M2 screws to attach the circuit to the housing base. For the top cover, I 3D printed 2 parts to cover the LED bars and ensure a smooth light distribution. With the top side assembled, the next step was connecting the top and bottom housing sections. While assembling, I noticed an issue with the housing design. The top side part had a very thin wall. I fixed the design and updated the STL files in my GitHub repository for anyone interested in using the improved version. Now all that's left is placing the battery cell and plugging the AC power adapter or the USB port. The circuit will instantly read the state of health and display it through the state of health LED bar. Similarly, the state of charge bar updates continuously during the charging process until the battery is fully charged. For testing, I used an old battery from an old laptop and the device performed excellently. It detected the battery's low health level accurately. Additionally, you can retrieve precise data from this device through the serial port and display it on any serial monitor, with the Arduino serial monitor being a great tool for this purpose. The device provides a regulated output, allowing you to not only charge a battery but also power other devices through the GST connector. I've also included a connection for an external NTC sensor in case you are using a battery with a built-in NTC sensor. Just be sure to cut the jumper if you are connecting an external sensor. The device is highly configurable based on your battery and input preferences. All the necessary details are documented directly in the circuit design for easy reference. That's it for today, guys. Feel free to drop your thoughts in the comments. One last thing, make sure you are doing electronics every day. It was Chris. See you next time.